Picture this. It is a cold, winter day in the heart of Alaska. You're walking north, from Anchorage to Petersville. This is usually safe, as you can walk along the road without getting lost. However, a sudden blizzard caused you to lose track of the road and lose sight of Petersville. This was regular though, so you came prepared with a compass, only to find you were walking in the wrong direction. Confused, you turn towards north, continue walking, and find yourself back in Anchorage less than an hour later. Typically, this would only happen because of bad navigation, but your compass wasn't lying, so what really caused your compass to flip? In the 11th century, the Chinese developed the first magnetic compasses, using lodestone or magnetized needles for navigation. This hinted that the Earth itself was a magnet, or it at least displayed magnetic properties. However, explorers in the 17th century discovered that the Earth was far from a perfect magnet. Magnetic north did not align with geographic north. Additionally, through the analysis of magnetic minerals in rocks, known as paleomagnetism, scientists found that the magnetic poles have reversed several times throughout history. Although this is rare, the opposite can be said for the yearly movements of the magnetic poles, averaging roughly 55 kilometers of displacement per year. The most widely accepted theory of Earth's magnetic field is known as the geodynamo theory. The Earth's outer core is made of molten, electrically conductive materials, primarily iron and nickel. As the Earth rotates, convection currents within the outer core are created by radioactive decay, heat transfer from the inner core, and the Coriolis effect due to Earth's rotation. These currents cause the movement of electrically charged particles, which generates electric currents, in turn creating Earth's magnetic field. However, these convection currents are not uniform. They vary in speed, intensity, and pattern. In turn, alters properties of the Earth's magnetic field. The magnetic poles are not fixed. This is because of the flow of molten material in the outer core, which changes over time. This results in the magnetic field lines to wander, leading to the observed movement of the magnetic poles. For example, the magnetic pole is currently moving towards Siberia. The field occasionally weakens, flips, and re-establishes itself, with the magnetic poles swapped. The magnetic field varies in strength or direction in Pacific areas, like the South Atlantic anomaly. This is a result of localized disturbances in the core's fluid flow. Therefore, the movements of Earth's magnetic poles live within a closed system, undisturbed by human influence. These minor yearly movements have many small impacts on everyday life. This includes the constant need to realign maritime navigation systems to match pole drift. Additionally, birds, sea turtles, and whales all utilize Earth's magnetic field for navigation during migration. Pole drift disrupts their magnetoreceptors, which allow for correct orientation over long, featureless distances. The position of the auroras, more commonly known as the northern lights, are also altered to match magnetic poles. However, none of these pose as great a danger as a magnetic pole reversal does. During a reversal, the Earth's magnetic field could weaken substantially, possibly to as low as 10% of its normal strength, causing increased solar radiation reaching Earth's surface. This weakening can last for hundreds or even thousands of years, and is when Earth starts to resemble the Fallout universe. In this time period, increased radiation will start to damage living organisms, potentially causing DNA mutations and higher cancer rates. These effects will be experienced worst at the highest latitudes, where the atmosphere isn't strong enough to absorb as much radiation. Geomagnetic storms are also amplified even further, with the deterioration of Earth's magnetic field causing widespread power outages and damages to satellites, making communication, navigation, and weather monitoring systems unreliable. So, we've established the consequence of a magnetic field flip, but is it about to flip again in the near future? Well, evidence suggests that we are long overdue of a flip. Over the last 5 million years, the Earth's magnetic field has reversed at least 20 times, occurring every 200 to 300,000 years. It has been around 780,000 years since the last long-term flip. However, there was a temporary flip 42,000 years ago, known as the Lachamps excursion, which was tracked by radiocarbon dating rings of ancient kauri trees preserved in northern New Zealand wetlands. Ice core records suggest such dips in solar activity, known as the grand solar minima, coincided with the Lachamps excursion, revealing that atmospheric changes could have resulted in huge shifts in the climate. Coincidentally, this was the exact time period when the downfall of the Neanderthals took place. You see, studies revealed that there was a rise in the use of caves by our ancestors around this time, as well as the rise in cave art. This might be down to the fact underground spaces offered shelter from the harsh climatic conditions. Before this, caves were a significant part of Neanderthal life, offering shelter and protection, but their reliance on cave-based living became a burden to their adaptability and long-term survival. Their competition, Homo sapiens, who had recently invaded Europe and Asia, adapted to climate changes by building shelters, allowing free movement across Earth. However, Neanderthals were tied to locations with caves, limiting their habitability options. Pairing this with Homo sapiens' communication skills, they could easily outcompete Neanderthals in hunting, foraging, and building tools. Cave dwelling led to small, isolated groups that were vulnerable to inbreeding, local disasters, and disease outbreaks. Climate warming after the ice ages in the late Pleistocene also led to a decline in many megafaunal species. For example, mammoths and woolly rhinoceroses, which were Neanderthals' primary food sources, ultimately leading the Earth's natural magnetic field to be the cause of the fall of the Neanderthals.